So we're on page 104. Page 104, we're starting what's called hypothesis testing. Every chapter for the rest of the semester will have hypothesis testing in it. Every single one. Today we're going to start with the basics of the terminology and the notation and so forth, and then we're going to do specifics, kind of like confidence intervals. We started off talking about what a confidence interval was, then we learned how to do it for proportions and how to do it for means and how to do it for standard deviations. So same kind of thing, but now it's not confidence intervals, it's these tests. And my first example is the same example I brought up all semester. Here I am again with this fair coin. Remember my imaginary fair coin? I claim it's fair, which means that the probability of tails is 50% or 0.5. Right, so that makes sense. If I flip it 200 times and I get tails 102 times, what can we conclude about my claim?
It's fairly accurate.
Seems pretty accurate. Why does it seem pretty accurate?
Because it's like 52%. Like, because you got half at least of tails.
Yeah, exactly what percentage of tails did I get? I like the way Kirsty's going with this.
51.
How do you get 51?
So I had 101.
Yeah, if I got 100 and was 102 out of 200, that's like my x over my n if you're talking about proportions, right? This ends up being 0.51. So I could say, well, I claimed that my coin was fair, which means it should have been 50%. And Kirsty's saying, well, it seems accurate even though that's not 50%, that's 51%. So why does it seem accurate even though that's not 50%? It's pretty close. It's not so far away that we're going, wow, what's wrong with your coin? So what we're finally going to learn in chapter 8 is how to decide how far away is far enough to say, wait a minute, your claim might not be right anymore. How can you reject that claim?
Isn't that like the margin of error?
It's kind of like the margin of error, yes. But instead of coming up with a confidence interval, it's just going to be that I have a claim, my coin is fair. And then we're going to flip the coin and then say, you know what, based on your results, that's too far away. I know that's too far away, so therefore I'm going to reject your claim, Jill. Or it's close enough, so we're going to say it looks like you might be right. So it's similar to the margin of error, yes. So that's part A. Seems fair. Seems fair. So what if I do it again with this coin, and now I get 21 tails out of 200? "21 tails out of 200 flips." That's 0.105, I think. Is that right? I got it in my head. It's about 10.5% of them are tails.
Seems unlikely.
Yeah, seems unlikely that would happen, right? Do we agree with Brian? If my coin really is fair, only 21 tails out of 200 flips, something seems wrong. So remember, my claim was my coin is fair. That was my claim. My claim that my coin is fair. Up here, Kirsty says, seems reasonable. I trust you, Jill. With part A, she was like, yep, makes sense. I think your coin is still fair, Jill. But down here, Brian's back there going, Jill, I'm not so sure I believe you anymore. You said it was a fair coin, but this is a really small probability. It's nowhere near 50%. The chances of this happening, we don't know the chances, we'll find that in a little bit. The chances of this happening are so slim to get such a low percentage that he's going to reject my claim and say, no, Jill, sorry, it's not a fair coin. That's the overview of what we're doing for every single problem from now on. Is my evidence different enough to reject the claim? This is different than 50%, but not that different. This is way different than 50%. Okay. Here comes the terminology. A hypothesis is a fancy word for the claim. So my claim was that my coin was fair. I might claim that the average age of an LMC student is 24. That's a claim about a mean. I might claim that the proportion of people who've seen the movie Sleeping Beauty is 72%. I mean, I could claim anything. I could claim that girls like Disney princesses more than boys. I could claim anything. That's a hypothesis. Then what the hypothesis test is this procedure that we're going to go through to either reject the claim or support a claim, depending on what we have. The rare event rule is the same thing we've been talking about all semester. What's the definition of rare in our case? Well, we talked about something that was rare.
Percentage of half.
A probability less than 0.05. I'm hearing it from 3 or 4 different places. When you have something, a probability of 0.05 or smaller, that's something that's rare. But look at what the rest of the rule says here. If, under a given assumption, the probability of an event is extremely small, we assume that the assumption was not correct. Like over here. We assumed that my coin was fair, but we pretty sure that the probability of getting such a low number of tails, it's so unlikely that we're going to reject that assumption. So my assumption must not have been correct that my coin was fair. I must have rigged it somehow. So that's been coming up all semester. And so now what we're going to start doing through in the middle of page 104 is the formal procedure. There are 5 steps to every hypothesis test. You have to include all 5 steps every time. I'm going to number them every single time in the beginning here. Actually, I'll probably do it all semester long to make sure you see all 5 of them. But you have to do all 5. The first one is to state the 2 hypotheses. There's always 2. There's the claim and then there's its complement. We call one of them the null hypothesis with an H0. H0. Sometimes you see that H sub 0, you'll hear someone call it H naught, H0. H0 is the null hypothesis, and it's a statement about a parameter. What are parameters? It could be a probability. It has something to do with the population. Might be the population mean, might be a population standard deviation. So it might be about mu or sigma or p. So that's what our claim is going to be. And then the alternative, which we call H1, is the statement that it's different from the null, so it's the opposite. We're going to talk about quite a few of those, kind of like the complement. So for example 1 that we talked about up above, we want to write my null and alternative hypothesis. My example 1 was the coin. Yes, ma'am?
The alternative hypothesis you said is like the complement, right?
The complement of the null, yes. What was my claim up in example 1?
That you have a fair coin.
That I have a fair coin. What did I really mean by that? Especially when we're talking about tails. A 50% chance that it'll be tails. That's what my claim really was, even though I didn't use those words. So how do I write that? What am I saying? Am I talking about a mean, a standard deviation, a proportion, a variance?
A probability.
A probability, but probability can also be called a proportion. Remember, proportion, percentage, and probability are all interchangeable. So my claim was that the proportion of tails was 0.50. This one was my claim. Do you agree with that? Sometimes you have to take the words and change them into symbols. Actually, every time we have to take the words and change them into symbols. That's the claim? So what do you think H1 is?
The probability doesn't 50?
It doesn't equal 0.50. How do I write that?
P with the line over?
Yeah, the line through the equal sign. Oh, not the, oh, I see what you're saying, P with the line over it. It's not the complement, it's the complement of this description. So either it is 50 or it's not 50. So the way we write it's not 50 is not equal to 0.50. I think that might be my phone I didn't turn on today. I just heard that one. If it wasn't mine, thanks for the reminder. I realize I never turned it off this morning. Here we go. If it was yours, you were in luck. I thought it was me. Questions on where that came from? So the very beginning of chapter 8, it's just practicing writing out the notation before we go through the whole process. We'll do that by the end of today. Okay, so that's the first part. So now example 2 says state the null and alternative hypothesis for each of the following. Okay, so example 2. The mean hourly wage for high school students is greater than $10.75 per hour. Example 1. Example 2. Yeah, let me just kind of write. So mu, because we're talking about the mean for the population. I'm not going to put an H0 each one yet. Greater than
And then
1075. We agree this is the claim? Now I want, before I write it up here at H0 and H1, I want to go back and read those two descriptions again because it's really crucial where everything goes. So H0 is a statement about a parameter, and it says that it's equal to some claimed value. Underline, highlight, circle that word equal. The equal sign always goes in H0. Even if it's not your claim, the equal sign goes in H0. In this example, it happened to be my claim and it had an equal sign, so I put it in H0. This is my claim this time.
you just put the equal sign underneath.
Ah, good question. Yeah, greater than or equal?
Yeah.
That wasn't the claim. If the claim had been at least 1075, then that would have been greater than or equal. So I can't change my claim. Because there isn't an equal sign here, it just means I can't write it here. I have to write it down here. That's all that means. So your claim is your claim. If it has an equal sign in it, you write it in H0. And then if you look at the alternative definition there, H1 always includes a less than, a greater than, or a not equal to. So H1 is everything but the equal sign. So H0 always has an equal, H1 never has the equal. So do we all agree that my claim has to go in H1 right now? So I'm going to write that here. You don't have to write the word claim next to the original one, but it really helps when we get to go to the conclusions in a little bit. So I always will write the word claim next to the actual claim. So then, the question is, what do I write for H0? What do I write for H0? What's the complement? If it's not
mu equals 1075.
aha. Kirsty says put mu equals 1075 up here. Now technically that's not the complement. Because
wouldn't it be like the meanest less than or?
less than or equal, right? Because either you're greater than 1075 or you're less than or equal to. Technically that's true, and we could write it that way, but all we care about in H0 is what is it equal to. It could be more, it could be less than that also, so it won't actually always be complements. You could write this, it wouldn't be wrong, I'm putting it up here in green. You could write that, but when we go to do the test, all we care about is what it's equal to. We don't care about the rest of it. So most of the time we're only going to write equals. Our book only writes the equal sign up here. Everyone okay with that subtlety there?
I just don't see, like, in the statement, it doesn't say anything about the mean.
Ah, but it does.
It says the
says the
mean
mean
hourly
hourly
rate is higher or is greater than
Right, that's what it
1075.
Mean
So it's greater.
hourly rate.
I like that, I like H1, I just don't like HO.
Ah, okay. Okay, sorry, I thought you were having trouble with this part.
No.
Okay, that part you got. I explain it anyhow. So H0 is the opposite. If I say it's greater than 1075 and you want to prove me wrong,
Right.
how are you going to prove me wrong? If it's not greater than 1075,
Well, it'd have to be less than,
or equal.
but so you're saying it's less than or equal to?
Yes.
Okay.
Technically, so what I'm saying is technically less than or equal to is the complement.
Yeah.
But the highest it could be before I'm right
Right,
would
right.
be the 1075.
And are we gonna figure out the exact number, or are we just gonna run with that?
The exact number of what?
Like the exact, because that's just the assumption that it's less than 1075, and it could be 1075, we don't know.
Well, that's what we're going to test.
Okay.
That's actually a good point. So it could be exactly 1075, we don't know. We're going to take our results and decide.
Okay.
The point I was trying to make is technically the complement is less than or equal to here, but we're not going to write the less than part, we're just going to keep the equal to sign, because that's the most extreme before you get to the other side anyhow. And when we do the process, all we care about is what the equal sign is. You could write it up there, it's not wrong, I won't mark you wrong.
So the equal sign always goes in H.
The equal sign always goes in H0. I don't know how many times I'm going to say that, so I'm glad you said it. Always goes in H0, every time. It doesn't matter if your claim is H0 or H1. See how I had one of each here? All that matters is the equal sign has to go in H0. Because we have to assume that something is true, we assume that something is equal to something. Kind of like the coin problem. I'm going to assume it's 50%. And kind of like what Brian asked, I'm never going to actually be able to prove that my coin is fair. I can't prove anything in statistics. Even here, remember the very first example where we got 51%? It wasn't enough for you to reject my claim that it was fair, but it doesn't mean my coin really is fair. Maybe I do get slightly more tails than heads. We don't know for sure. It's kind of like when you go to court. The person goes in and claims that they're innocent, and then say you have some evidence but not enough to convict them, right? It doesn't mean they're innocent. It just means you didn't have enough evidence to convict them. Maybe they did it for all we know, right? You're never going to prove innocence. You may not have enough to prove someone guilty, but you can't prove the opposite. I'll refer to court a lot as we go through this. Other questions? These are good questions so far. Okay, so that was example 2. Let's flip over and look at example 3. Let's do it again now for the standard deviation. The claim is that the standard deviation of men's height is equal to 5.4 inches. Where do I write that? H0, because
It's got the equals.
has an equal sign. What symbol do I use?
The sigma.
Sigma. Always talking about the population parameters. You're never putting a claim about a sample. A sample you can actually calculate. That's our claim. Standard was it 5.4? Yes. That's our claim here. So what goes in H1?
Same thing with slash and equals.
Same thing, but they're not equals to. So writing the claims is actually the easiest part. The most important thing is exactly what Evelyn said. You have to remember that the equal sign goes in H0. Now that's step 1. So step 1 of any hypothesis test is to write these two claims, the two hypotheses. The one claim and the two hypotheses. Step 2 is to identify and find what's called a test statistic. Just make yourself a little note that we'll learn that a little bit later. It's too early for us to get to there. What is that? Sounds like a donkey. Kind of like a donkey out now. I'm hearing things apparently.
Someone was laughing.
Was it someone's laugh that sounded like a donkey? That wasn't very nice of me. Look at it. A little note that we'll do that later. Step 2. Step 3 is to find either a critical value or a p-value. We're going to talk about both. They mean the same thing essentially. Kind of goes back to Ariana's question earlier about isn't that like the margin of error? It's the same kind of idea. We're going to be doing both. There are certain tests where you need the p-value and certain tests where you need a critical value, and I'm going to be explaining them both to you as we go. But we used critical values before. When did we use critical values? Z-scores, when we were looking like for the formulas, you know, on confidence intervals where you had to find the Z alpha over 2. So critical values kind of mean the same thing here, except you're not always going to have what we call two tails. So we're going to talk about the p-value method a little bit. Right now, we're going to find the critical values that go with these examples. And so I'm going to show you a picture and then show you what we mean by the critical values. So I'm on example 4, in the middle of page 105. Example 4, they gave me these two claims. I'm just going to rewrite those so I can point at them here in a minute. So we're testing some claim about a mean. Notice there's an equal sign up here. And there's a less than sign there, which makes sense based on what we were doing. And they gave us this little alpha. They gave us this little alpha up there. Alpha is called the significance level. We used alpha before also, though. What was alpha in chapter 7? We used it to find the cutoff, but do you remember what the alpha by itself was?
It was the amount of both tails.
Yeah, the amount of area in the tails. Perfect. Remember that? The area in the tails was alpha, then we cut it into to see what it was in each tail. So alpha is still the area in the tail or tails. It might be one tail, it might be two tails, which is what we're about to talk about. Yes, ma'am?
What did you say alpha stood for now? It was the
Significance level. The significance level. That will be coming up soon, but I'll tell you now anyhow, it's called the significance level. So remember we started today by talking about our definition of rare is anything smaller than 0.05? Our definition of rare is going to change based on what we're doing. Imagine if I'm a doctor. I don't want there to be a 5% chance that I'm wrong when I go to do some procedure on somebody. That's a pretty high likelihood that, what if it's a life or death situation, right? I don't want there to be a 5%. I want it to be a much smaller chance that I'm wrong. So sometimes we say we want something to be really rare before we make that decision. So maybe we're saying that at this point, 0.01 is our definition of a really small probability. We want something to be really rare before we make that decision. 5% is not. If we're just trying to make a decision about, sociology or something, that's one thing. But if you're trying to make a health decision, you don't want to have a probability that you're wrong be 5%. It might be a little too high. So this 0.05 that we're used to is going to change. So now we're saying 0.01 is our cutoff for a small probability for this problem. So in terms of a picture, we're talking about normal. If we're talking about z's, we have 0 in the middle. If we were talking about this situation here, we would have been talking about 42.5 feet in the middle, right? Where would I have to be to show that H1 is a correct statement? Looking at this picture on the right, where on this number line would I have to be to show that this is correct?
42.5.
H1 is correct, not H0. So where on this number line would I be to show that the mean is less than 42.5? Somewhere to the left. Like right here?
Yeah, maybe.
Could be.
Anywhere.
Anywhere to the left? Ooh, remember my example about the coin when I got 51%? And you said that's not that different.
So at least 2 standard deviations.
Okay, so it used to be at least 2 standard deviations away, but do you agree that really close to 42.5 is not real different? It could have just happened by chance. To have a really small probability of it happening, I need to be pretty far to the left. Pretty far away. The definition of how far away is given in our significance level. It says, I want you to be far enough away, I'm just going to make a little mark right here, I want another color, so that the area in this, from here over, that's far enough away with this tail, I'm lost in my necklace here, the area in this tail is exactly your alpha. And the question is, what is this cutoff right here, right? So there's some number right there, similar to what we've done before, that that's far enough away that there's only a 1% chance that you could be past there. Okay with that picture? Yes, ma'am.
I thought alpha was like both tails.
Ah, yes. So in confidence intervals, alpha was always these 2 tails because we had this percentage that was in the middle. So what we're going to learn now is we have 1-tailed tests and 2-tailed tests. In this case, if you want to prove that this is true, the only way you could do it is to be to the left. You couldn't be way out here higher than that. That wouldn't prove that it wouldn't support your 42.5 claim. So based on your H1, you might have 1 tail or 2 tails. So alpha always was 2. We're going to see some of those in a couple minutes here. But sometimes there's 2 and sometimes there's 1, and I'll make sure we're clear on how we know. But the reason there's only 1 tail is the only way to be here is to be just to the left. So alpha is the whole thing in that whole tail. And so when you're looking for a critical value, we're now talking about z's. So we're really asking the same question here. What is this z right here that gives me the 0.01 in that tail? I didn't hear you say.
We looked it up.
We have to look it up, either on our calculator or on our table. But do we all agree that that's really a review problem?
Yeah.
Find the z that cuts off an area of 0.01. So critical values are still the same critical values we did before. So the critical value for this one, what am I going to do?
Is it a confidence level then, like, or isn't it like a 0.99?
We can't look at the confidence level Because confidence level, remember, are two-tailed things where you have a cutoff here and a cutoff here. So you can't look at that bottom corner of page 5 anymore, darn it.
Would it be the lower and upper? Would we do like the upper is like 9, 9, 9, 9?
If we were looking for this probability, if we were trying to find this area, I could do normal CDF and do from -999 to this number. Or I would do inverse norm. Remember, inverse is when you have the area and you don't know the cutoff. Same thing at the bottom of the chapter 6 on your packet, right? If you have the area and you're looking for the cutoff or the critical value, it even says use this to find critical values. So what would I do with my calculator?
-9999. No.
Wait, hang on, which one are we using?
Inverse norm.
Inverse norm, and if you look on your packet, what does it want to know first?
It wants to know the area to the left.
The area to the left, which in this case is to
0.9.
the left, careful.
Oh,
Just 0.01. To the left.
Would it be mu is 0?
And mu is 0, standard deviation is 1, because we're looking for z's.
Standard deviation.
Yes, because we're looking for z's, the mean and standard deviation are 0 and 1.
Does it spell it out? Does it spell
Yes, ma'am.
So say if this was to the right, then would it be 0.99?
Yes, if I had a 0.01 tail over here to the right, then I'd have 99 to the left. We'll see one of those coming up as well. What's his answer?
-2.333.
-2.33?
Yep.
Does that make sense to have a negative z in this case?
Yeah.
Why?
To the left.
Because I need to be to the left of 0, right? I need to be somewhere to the left. That better be a negative answer. So let's say Kirsty had accidentally punched in the 0.99 because she wasn't thinking about the left and the right. If she had, her answer would have been positive 2.33, which is over here. And that would have given her a hint like, wait a minute, that can't be right. It's supposed to be over there. So I keep telling everyone in the math lab, make sure you draw the picture to at least decide if your answer makes sense. Are you in the right location? Questions on that?
So when we see that, like from example 4, when it's giving us an alpha, is that, do we have to find the z-score?
When it asks for the, so they'll always give you an alpha.
Uh-huh,
If it asks for the critical value, that means find the z-score.
okay.
And critical values will change as we go along, but today it means a z-score, yes. So it's not that they'll always give you that alpha, but the directions are up above. You might want to circle those or highlight where it says find the critical values, right above example 4. We're finding critical value. So this is my critical value right here. All right with that one? Okay, so let's do the next one. Example 5. Example 5. Oh, it's the same one I have here. How convenient was that? Alpha equals 0.05. I'm going to also write up here about alpha. Area in your tail or tails, depending on which one you have. Keep that up there for the rest of today. So in this case, because alpha is 0.05, the area in our tail or tails is 0.05 instead of 0.01. Now, this one is a not equal to claim. If I claim it's 50%, how are you going to prove me wrong? By it not being 50%, where am I then on this number line if it's not 50?
Either direction.
Either direction, maybe I'm higher or lower. We agree I could be higher or lower to prove me wrong? So this is what we call a two-tailed test. You can either be all the way over here, far enough away from the middle, or you can be all the way over here. I'm going to move out of the way so you guys can see it. I could be here or here. Either one is far enough away. If I'm over here, I'm far enough away. If I'm over there, I'm far enough away from what we expected.
So that's when we have 2 tails.
This is when we have two tails, because to prove something's not equal, it could be higher or lower. Right? If I come in right now and I say, hey, I'm 45 years old. You want to prove me wrong, all you have to do is either give me any number bigger than 45 or less than 45. Any of those would work. Right? So higher or lower than the middle. Now, what's the area in each tail?
Would you take and divide by?
Yeah, we take that 0.05 and divide it by 2, just like we did before, because the area in all the tails together is alpha. 0.05 is the total area, so each one of these tails, bless you, is alpha over 2, just like we did for confidence intervals. 0.025. So that was going back to Carrie's question earlier. She's like, I thought it was two tails. This is an example of where it is a two-tailed test. In this case, we actually have two critical values. This one and this one. There are two critical values in this problem. How do I find those?
I feel like it's the same things that we've been doing.
Yes, I'm so glad you did.
Just do CDF, right?
Yeah.
Okay, is it
Is there high
CDF?
or low, or-
No.
No, it's still
That's
effort.
Z-score.
I'm still looking
just
for
look
the
at
Z-score.
scores.
So that's what Kirsty said. I feel like it's the same thing we've been doing. Subtract what from one?
One
Oh, you skipped the
from
inside.
the area to the right.
Well, let's do one at a time. Let's find this guy first.
Why didn't you just do
0.025, the inverse norm
That's us.
gives you the negative 1.9.
So tell me what you just said, Brian?
If you do inverse norm, you do 0.025, that will give you the Z-score for the left tail.
I like what he's saying. Is that what you were gonna say?
I was gonna say, like, when you do inverse norm for the left one, you just make it positive on the other side.
Uh-huh, so she's finding the shortcut to find the other ones. Let's hear what, you guys all hear what Brian said? The same thing we've been doing. We know the area to the left is 0.025. We're looking for the critical value, that cutoff. So again, it's just an inverse norm problem. 0.025, 0 and 1. Should be negative 1.96, I think.
Yep.
Yeah, and divide by 2.
And then.
But we don't divide that by 2. That is our Z. The dividing by 2 is what we did over
We'll
here.
do the positive one.
But that's what Phoebe was saying also. Because it's Z's, remember zero's in the middle? So if this one's negative 1.96, that one better be positive 1.96. With Z's, they're always balanced. One's positive and one's negative. Remember when we had chi-squared, you had two different numbers? We'll see that coming up again at the end of chapter 8. Everything we did with confidence intervals, we're going to do again with tests now. So I have two critical values. These are my critical values for this case. Bless you. Yes.
On online, will it just have like separate by commas?
Yeah, it'll say list your critical values if you've got more than one separate by comma. So it won't tell you if you have one or two. So if it was these problems online, it would just say list your critical values. In this case, you would only put one of them, and in that one, you would list both of them with commas. Yes.
And like, they'll say like when you know it's a one tail, they'll say like, oh, it's less than or greater than this or
Yes.
less than that.
That's what tells you it's one tail. Exactly. Yes, sir. Oh, beautiful. Did you hear what her question was? Like, how do you know it's one-tailed? And what she said was it's either going to be just less than or just greater than. That's the only way to be one-tailed, on one side or the other. Because if it's a not equal to, that's when you can go either direction. So look at what it says for example 6. It doesn't even give me the less than or greater than. It gave me an alpha of 0.05 again. And all it says is H1 is right-tailed.
Would we find the critical value and if it's a greater than or equal
Yes.
or less than?
Oh yeah, is it a greater than or a less than is the question.
Greater than.
So I heard a greater than over there. What were you going to ask or say, Christy? Oh, okay. Why is it greater than?
Because it's right there.
Because it has to be to the right. If you're to the right, it's greater than the middle, right? So you want to get used to that language where sometimes they'll say it's a greater than, sometimes they'll call it right-tailed. This one was a left-tailed problem, right? Because this tail was on the left. If it's right-tailed only, we're looking for this little tail over here on the right, and we want to know what this z is. Which means that this must have had a greater than sign in it. That's the question I was just asking and what Cristiano was just talking about. We agree that it must have been a greater than if we ended up being on the right? Less than is on the left, greater than is on the right, not equal to is two tails. What's the area in this tail? 0.05, because I only have one tail in this case again.
Do we divide it?
I didn't hear you said.
Do you have to divide it again?
We don't, because we don't have another tail. So that's the really important thing here. The area, this was a 0.05 in this example 5. They had the same significance level. 0.05, 0.05. But here, because it was a two-tailed test, we had to divide that area into two pieces. So each tail was only 2.5%. Where over here, it's only the greater than, so that tail's 5% all by itself. So you can't just say, oh, every time it's 0.05, I get the same numbers, which is why I was telling you don't look at the bottom of page 5 anymore, because those are only for two-tailed tests. So how am I going to find this critical value?
You take it, you subtract 0.05 from 1, and then put that in inverse norm.
Yes, we need to know the area to the left to use inverse norm. If I have 0.05 on the right, the complement of that is 0.95 on the left. So then I'm going to do inverse norm of 0.95.
$1.65.
1.65?
Sounds familiar.
Yeah, sounds familiar. It's probably actually 1.645 to be exact.
Yep.
According to the paper, it's on there. It's positive. Does that make sense?
Yeah.
Yep.
Why?
Because
It's on the right.
Because it's to the right. Right? Make sure you know what you're finding. All we're doing, excuse me, in these last few examples is finding critical values. The hardest part is we're going to spend quite a bit of time just talking about this is how you write your hypothesis, this is how you find critical values. You need to know what they represent because pretty soon we're going to put it all together. Yes.
How would you write the HO and H1 for this one?
We don't know what it was. They didn't give us any information. It could be anything. It could be about standard deviation.
Right.
I claim the standard deviation is 2, it's greater than 2. It could be about a mean. The mean is 49, the mean is greater than 49. So we don't really know because they didn't give us any information, but it could have been a lot of things. And so no matter what it was, if we're looking for critical Z's, we're going to do the same thing no matter what.
Right.
So that's the important part here is sometimes all you care about is the symbols, not the symbols here, but the symbols here equal, greater than, less than, so you know if it's left or right
Right,
or
it'll tell us
tails.
what application. it is.
Exactly. Yes.
We don't need to do the problem ourselves.
You don't need what for this problem?
We don't know this and just like that.
Yeah, they're not asking for anything other than the critical values. All they're asking for is what I put in these little boxed answers down here. The pictures were just to help us understand how we were going to go about finding those. So the 5 steps that are always required is when you're doing a complete test. Right now we're still doing little bits and pieces to understand the little pieces. Questions? You think we got critical values down? Kind of like a review. Okay. Excuse me. Step 4 is going to make a decision on whether or not you reject your H0. So let's read step 4 first, and I'm going to talk about it a little bit more. So step 4 says state the conclusion about the null hypothesis. Now I can't say this enough. I don't have it written here, but remember my first few examples where I wrote claim, sometimes it was next to H0, sometimes the claim was H1. The decisions you make are always about H0. Imagine you're going into court. Someone's on trial, they claim that they're innocent. If you're working for the prosecutor, you really are trying to prove that he's guilty. But if you're his lawyer, you're trying to get him to be not guilty. So the claims are different based on whose side you're on. But the jury has to decide if he's guilty or not. For the jury has to decide whether or not to reject his claim that he's innocent. So no matter which lawyer you are, the decision is, are we going to convict him or not? And so our decision is, are we going to reject H0 or not? Then we'll decide about the original claim. So that's what it's talking about here. We're always going to decide what to do with the null hypothesis. The only thing you can do is reject it or fail to reject it. Remember my coin I started with? I got 51% tails. That wasn't enough for you guys to reject my claim that it was fair. Right? You said, I'm not going to tell you you're wrong, Jill. It seems close enough. So in that case, you would have failed to reject my claim. It's not different enough to reject it. Where when it was really extreme, I can't remember what it was, 10.5% or something, that's enough to reject the claim. And the way we're going to make that decision is by looking at either what's called a p-value, which is a probability, or the critical value. And then we're going to make a decision. So let's flip pages here. We'll look at these examples up here, then we'll take a break and do a lot more of them after that. The note on top of page 106 is that you're only required to do the critical value method or the p-value method. I'm going to continue to show you both so you see how they're related and that you understand them both. You'll end up with a preference. So let's look at example 7. There's not a lot there, but there's a lot to do. So we'll just do example 7, then we'll take our break and then do the other one afterwards so that it'll be fresh. So all they gave me was H1. H1 is P greater than 1/4. They gave me a test statistic. Z equals 2.79. We'll talk about that in a minute. And they gave me an alpha. We're used to seeing those now. That's all I have. And the directions were on the previous page, unfortunately. The directions were to find the critical values and the p-values to make a decision. Make sure you make a note that the directions are on the previous page, otherwise you're going to be like, what was I doing? It's at the very bottom of page 105. It says step 4, where it says find the p-value and the critical values in bold. So let's fill in some gaps here. I'm going to write another color since we weren't given them. I think I know what H0 is.
P equals 1/4.
P equals 1/4, right? H0 has to have an equal sign. So it better be P equals 1/4. That was kind of given to us in disguise. Is this a left-tailed, a right-tailed, or a two-tailed test? Right-tailed. How do we know it's right-tailed? Greater than. So let me draw a picture for this guy. Here's my picture. If I'm talking about Z's, you guys have all just decided it's a right-tailed test. What's the area in this tail over here? 0.01. 0.01 because that gave us our significance level, our alpha, the area in the tails. Could you find this critical value? We're practicing those.
Yeah.
Please tell me yes.
Yeah.
How would I find that critical value? Inverse norm of 0.99. You always tell your inverse norm the area to the left. What did we get? 2.33. So this number right here is 2.33 on my number line. Now here's where it gets confusing. There's a Z over here and you're going, what is that, Jill? What the heck is that? We're going to talk about that in a minute. And there's a Z over here. I like to distinguish my critical values from the other Z's that we're going to get, which are called our test statistics, by putting stars on them. You don't have to, but the whole point is you need to know which one's your critical value and which one's your what's called a test statistic. And they're both Z's. You need to know which one is which. kind of like if I give you two means, and one's from your sample and one's from your population, you have to know which one is which and label them correctly. They're both means. These are both z's. So I like to put a critical value with a star on it. So all these ones we were practicing, I would have put a star on it if it was in the middle of a problem. Little stars on them for critical values. Your book won't make it a star, but it helps to know which one's which. Okay, so here's the big picture now. We've decided that this is the cutoff, that anything past that is far enough away to be unlikely and to be rare. Anything past that is rare. We're going to talk about how to come up with this later, but our test did some work and came up with this test statistic. Our results came up with this z-value. Where is that on my picture?
Past 2.3.
Past 2.33, right? 2.79 is over here somewhere. It's over here. In that, what I like to call the rejection region. The rejection region. Our book calls it the critical region. So what we're saying is anything that passes this line is far enough away to reject H0. So we have something that was far enough away. We have our critical value. We compared our test statistic to see if it was in what's called the critical region. I like to call it the rejection region. So if you go back to our directions, which are unfortunately on the previous page, it says find the p-value, which we haven't done yet, and find the critical value, which we did, and then state the conclusion about H0. So what's happening is P is supposed to be 1/4. Supposed to be Z in the middle, right? I'm so far away, though, that I'm going to reject that hypothesis. So my conclusion in step 4 is going to be to reject H0. That's all you're ever going to write. You're either going to write the words reject H0 or you're going to write fail to reject H0. Yes?
Why you reject H0?
Because this critical value is what defines the cutoff for what's rare. So anything between here and here is different than what we expected, but not that different. But eventually we're saying how far away is far enough to really be unlikely to happen, and this is our decision. If we get any Z past that, that's too far away.
To be able to see, so that Z is further than what we thought, right?
Exactly. So we compared our test statistic to our critical value. So this is the critical value method it's referring to.
That's how you decide?
That's one of the ways you can decide, yes. There's two ways to decide. One way is called the critical value method. The other way is called the p-value method, which we're going to do probably after the break because I can feel the energy level dropping.
This is the critical value.
This is the critical value method. Let's talk about what I'm doing. If your test statistic is in your critical region, then reject H0. That's how you make your decision for the critical value method. So the test statistic right now was handed to us. Actually, most of the time for us, it will be handed to us by our calculators, which is nice. But the test statistic is what comes from your sample results. Your sample gives you some calculation. And then we say, well, how does that compare to our cutoff? Is it far enough away to reject our assumption that that was true? Because what we're saying is if it really is 1/4, it's almost impossible to end up that far away. That language make sense? Okay, let's take a 10-minute break. We'll come back, we'll do the p-value method here, and then we'll do it for a couple more examples to make sure we get it. Lots of vocabulary. Did I not warn you about this? So here's where I hope you are. are. We just finished the critical value method for example 7.
But I can't remember it.
You all listened to my directions and copied this down on the top of page 106. I need you to know what the p-value is, otherwise it won't make sense.
Are we gonna use the p-value on example 8 or example 7?
We're going to do it on example 7 first, then we're going to go on example 8. So this picture that I have right here, this picture that I have here is just the same picture again from example 7. Oh, now we're ready. Okay. So we did the critical value method for example 7, where we decided, we have a test statistic of 2.79. Is that far enough away to reject H0? So I'm going to do the same thing again, but I'm not going to find the critical value. I'm going to find what's called the p-value to make the same decision. Okay? So the important thing is knowing what the p-value is. The p-value is the probability of getting your test statistic, which remember that was our 2.79, getting this result or more extreme. What do I mean by more extreme? Higher in this case, because it was a greater than claim. Way back over here, still doing example 7. So this probability right here, this is example 7 again. I don't know if you want to do it on top of the other one. This area right here equals the p-value. I hope, I haven't finished grading the test yet, I hope that you know how to find that area. From 2.79 out here forever.
Normal CDF.
Normal CDF?
That would be your lower bounds.
Yes, this would be my lower. My upper would be 9999. See how, well, this is now, you know why we practiced all of chapter 6? So my p-value is going to be normal CDF, 2.799999, 0 and 1. That's why you had to have chapter 6 down to go on.
0.0026.
0.0026?
Yep.
My picture clearly shows it bigger than that, but I wanted to make sure you saw it. So it's a really tiny little sliver, is what that says, right? Really small probability. So when somebody claims that the proportion is greater than 1/4, or excuse me, they claim that the proportion is equal to 1/4, there is only a less than 1% chance of our results happening, which means our results are really rare. They're so rare that that's enough evidence to reject the claim. This is a small p-value. What's our definition of small? She quietly says 0.01. She's totally right. Up till today, small was anything smaller than 0.05. Today, it's your significance level. Today, it's anything smaller than 0.01. 0.01 was our significance level in this problem. So any probability smaller than that would tell me that my results are rare. And again, because that's rare, in this case, 0.0026 is less than 0.01. Or we could say, in general, it's less than alpha. Less than alpha. Because that's true, we again reject H0. Squeeze that in right here. Wait, let me answer questions first.
So anything less than the given significance level, which is alpha, is considered rejected.
Yes, any p-value less than your significance level tells you to reject H0. Evelyn's all over this place. She's asking perfect clarification questions.
Can you repeat that?
I'm going to write it down right here. So I will repeat it and write it down there. So the p-value method. if your p-value is less than alpha, reject H0. When you have a small probability, something's really unlikely to happen, and then it happens, that must be a reason to reject your original claim. Now, we don't have the whole context here, but if the probability, the proportion really was 1/4, there's a 0.0023 chance that we would have gotten our results. Something really rare happened, so maybe that assumption was not true, so we're rejecting it. Question. See brains thinking, processing. No questions? Yes?
You can use both ways?
You can use both. And I'm going to actually overlap them right now on that picture to show you how they're directly related.
So will we still follow the same? I'm trying to think of how to ask this question. Because one of them calculates probability and one of them calculates the z-value.
The cutoff, yeah.
Yeah, so is that going to be critical later on in this chapter?
There will be one chapter where you have to use critical values. But almost everything we do from now on, we'll also be able to get p-values handed to us on a silver platter off our calculator. So I'm never going to require one or the other, if you could do both. But I need you to understand how they work and how they're related, which is what I'm about to show you, so that then you understand why either one tells you the same thing. As we get to the part where you have to do one versus the other, I'll make sure to point out and say, we only can do p-value method here, or we can only do critical value. Because this area we just found was 0.0026, right? This red area. Now our critical value, which we found behind me over there, was 2.33. It's really big, I know, but I just make it so we can see it. What was the area, I'm going to make a polka dot just so it's not all scribbled over. What was the area inside the blue region?
The rejection.
Yeah, what was the area inside the blue one? From the critical value over. Someone just said it. 0.01, right? The blue one is 0.01. This whole blue tail is 0.01. So we're saying that anything past here is going to be extreme and tell us to reject. Well, our 2.79 was past there. That's how we made our decision earlier. And notice this red area is definitely smaller than the blue area. So if you're past it, you're guaranteed your p-value is smaller. And if your p-value is smaller, you're guaranteed that you're past that cutoff. So they are directly related. One of the most frustrating things about my stat lab is you might do the p-value method and say, oh, if my p-value is small, I'm going to reject H0. And then when it asks you why you rejected, multiple choice, you love those problems, one of the options will be, because my test statistic was in the critical region. Even if you don't know that it was in there, if you're rejecting H0, you do know it had to be in the rejection region, even if you didn't find the critical value. So you want to make sure that you understand what this language and this language are both saying and how they're related. Where's that go?
So the critical value gives us where the cutoff line begins and ends, where if it's past this line, it's automatically rejected. But then the p-value gives us exactly where it occurred in the rejection?
Close. Close. So the first part was totally right. The critical value, which in this case was 2.33, tells you exactly what cuts off the area of alpha. So this gives us exactly 1%. And so that's our cutoff for any number past there is extreme enough to reject. The p-value is the probability of actually getting your test statistic. My 2.79, how likely is it to get 2.79 or more? It tells you how likely that is. So you're deciding whether or not your results are rare. Does that help?
Yeah, totally.
So it's either, are my results past the cutoff? That's what this method is doing. Or is it, are my results rare? Really, they're the same question.
This is 0.0026 is less than 0.01.
Yes. These are good questions. Okay, Ready to try example 8 now? Now we beat this one up? No, she's not ready. You have a question about this one?
There's just a lot.
There is a lot. These are the two things I want you to make sure you have written down. And if you don't understand them, I want you to keep asking questions in your own words and keep getting me to rephrase it till something clicks. Pointing pictures and so forth. Okay, we're going to go on example 8. Even though Christiana says she's not ready. Example 8 says we have a two-tailed test. We have our test statistic is z equals 1.75. And we have an alpha of 0.05. So let's do example 8. Maybe we'll do the p-value method first this time. Example 8, I have a two-tailed test. So I don't know anything about H0 and H1, or do I? If it's a two-tailed test. It's equal and not equal is what Carrie's telling me up here. We don't know what the symbols are, because they didn't tell us that part. But we know, we don't know if it's a mu or a p, right? But we do know it's a not equal to, because two-tailed member is not equal, greater than or less than. So we were kind of given that. We can't really write the rest of it though. They're not asking us to. They're just asking us to decide if we're going to reject H0 or not. So we have a two-tailed test. We have a test statistic. Of 2.75, let me write z equals, or 1.75, excuse me. And we were given an alpha of 0.05. So that's our definition of what makes a small probability for this problem, something less than 0.05. That's all we have. And they want us to decide if we should reject H0 or not. That was the directions on the previous page we talked about earlier. We want to know, should we reject H0 or not? So we either have to decide, is that 1.75 in the critical region? Or we have to decide if its p-value is small. We have to do one or the other. Or both. I'm going to do both to make sure we understand how they both work. So I'm going to draw a picture. Here's my normal distribution. Let's do the p-value method. What do I want to do with my 1.75? Here it is.
Don't we want to find the value of the tails?
The area of the tails, yes, exactly.
So then you would take 0.05 and divide by 2 as you find the area.
Yes, if we're doing the critical value method. So let me back up a second. Last time I did the critical value method first, then p-value. You want me to do them in the same order or opposite order? It doesn't matter.
No, do the p-value because it's still kind of confusing.
Okay, we're going to do both anyhow, so I just want to make sure we know which one we're doing. So I'm doing the p-value method first. So what is the p-value?
Probability.
The probability of getting my result or something more extreme.
So normal CDF.
Let's draw the tails first though, but you're right, we're going to do normal CDF. So either getting 1.75 or more extreme. But here's the catch. There's a big but there, big but. If it's a not equal to be that extreme, I could either be that far away on the right, or I could also be on the left. I actually have to consider, what if I'm over here at negative 1.75, and I happen to have the same tail on this side? Those are supposed to be the same size. They don't look the same size from my pictures. Use your imagination. I can try to fix them a little bit, but I don't know if it works. I'm not an artist. Yeah, there. Now they're closer. Just keep scribbling until it looks better. So because it's a two-tailed test, you have to consider how likely is it to be this far away on the right or on the left. Now I'm still going to use normal CDF. I can use normal CDF to find either one. I'm gonna find this tail with normal CDF. How am I gonna find the area in that tail with normal CDF?
1.75,
The one seven.
999.
Starting at 1.75, going to 9999, 0 and 1.
Equals 0.0401.
0401. Bless you. Do we agree with him? What is that?
That's only
One tail. This little guy right here, that's what we just found. He's 0.0401. That's the area in this tail. Here's a trick question. What's the area in this tail?
Negative 0.0401? Or is it the same?
It's the same, right? It's not negative because they're areas, right?
Yeah.
That's why I made the point to say they're the same size.
I got
If
it.
this one's 0.0401, this one's 0.0401. So what's my p-value?
0.0802.
Well, how'd you get the 0.08? What'd you do?
Add it together.
She's adding these together? Or I would just double it? My p-value in this case is 2 times that one tail, or you can add it to itself. .0802. That's the probability of all the red combined. Does everyone understand why I doubled it?
No.
No.
2 tails.
Okay, so do you agree that we found this one right here, Kevin?
Yeah.
That's 0.0401? Well, my p-value is the probability of being over here or over here. So I have to take this area and this area, and since they're the same size, instead of calculating this one and then calculating that one, I just said they're the same, so I'm just going to double it because of the 2 tails. Does that help? Anybody else want to ask that question a different way? Okay, so the whole point here was, do we reject H0 or not? Do we reject H0 or not?
No.
She says no.
I say, I think we do.
He thinks we do.
Let me see.
I got 2 people saying yes and 2 people saying no. I got 30 other people not saying anything. Makes me a little nervous. Let's read this out loud together.
0.04 is inside of 0.05. So
Hang on, what was my p-value?
0.0.
I hear what you're saying, Brian, but this was my p-value.
you have to do it like that?
Yes,
Yeah, all right.
that's the important thing. Your p-value is the area in all your tails, however many you have.
Yeah, I got you. Yeah, you're right.
I got 1 person converted. If your p-value, 0.08 something, is less than alpha, what was alpha in this case? 0.05. Is my p-value less than 0.05?
No.
No, so I cannot reject H0. So what I write is fail to reject H0. It's kind of like in court. You either you either convict someone or you fail to convict them. You can't ever say they really are innocent. So you can't ever say you support it. You just can't reject it. So step 4. I'm sorry. Say that again.
Like it's like pleading no contest. And it's like,
Yeah.
that's easier.
Right. Yeah, exactly. I'm not really saying it. It's kind of a statistic you get a little bit weak, where you can't ever prove anything with statistics. You can support some things or not reject some things, but you can never make a clear, definite line. So I just did the p-value method here. Yes? Okay with it now, we think? I caught some of you on that 2-tailed thing. I know it's a little bit weird. The good news is when we do these on our calculators, when you do a whole test from scratch, it'll hand you the p-value. Say, oh, here's your p-value. You don't even have to calculate it on your own. It's actually pretty nice. Once you understand what it's doing, it's a lot better. So let's do the critical value method for the same problem. I want to do my critical values in green, just so I don't get confused. If I wanted to find the critical values, let's back up and think about that. Where do they come from? Where do the critical values come from? They come from the z's. They're z's. How do I get those z's?
Divided by 2.
Divide what by 2?
The alpha.
Point of.
The alpha. I have to take my significance level and make some tails that are both 0.05. Oh, sorry, both add up to 0.05. I heard what my brain said, and my mouth said right the same thing. So I have to divide it in 2. So alpha equals 0.05 divided by 2 is 0.025 in each tail. We did this earlier, I think.
Yeah.
So maybe I would be like right here, where this area in here, this is my Z star, gives me a little area, a green area of 0.025. Can you see this, Nick? Kind of small. Take your alpha divided by 2. Your critical values always come from alpha. And then similarly, there's going to be another one on this side over here that has the same area of 0.025. 0.025. So Z star. Squeeze it in there. How am I going to find those Z's?
You use inverse norm,
Inverse norm.
that would be 0.975.
If you're doing this one, yes, it'd be 0.975. I usually do this one first because it's on the left, it's easier, but you're right, you could do that one. Inverse norm of either 0.975 or inverse norm of 0.025.
And 0 and 1.
And 0 and 1. Can you write that down? It's really strong. I'm doing the left one first. You should get negative 1.96.
Yep.
So this number right here is negative 1.96, right there. This number over here is, guess what?
Positive.
Positive 1.96. What are the critical numbers? What do they tell us? Okay, go ahead.
What's the green, like, in the chart?
The green is the area of our significance level.
Why did you put it less than the red?
Good question. Why did I put it less than red? I put it there because it had to line up with 1.96.
Oh, maybe I was confused because you colored it in first before we got the numbers? Or I wasn't looking or something?
We did. I mean, I drew it roughly where I knew the answer would turn out. But I just knew that I had to find the critical line, so it helps me to draw the picture first just so you see what you're looking for. You could have guessed in the wrong place and you just would have had to adjust it.
Okay.
But it does turn out to be that it's exactly negative 1.96 and positive 1.96. You may or may not, if we hadn't done the red yet, like if we did this method first, the red wouldn't have even been there, so it wouldn't have mattered. But I like the fact that she's asking this question. So my question was, what do the critical values tell us?
Isn't that the automatic like cutoff of where it's going to be rejected?
Yes, any test statistic past here would tell me to reject H0. So anything from here over is the critical region, is what our book calls it. I call it the rejection region. But look, this red dot was my test statistic. Is my red dot in that green zone? No.
So you can't reject.
So I can't reject. It's not in this green zone either. So I can't reject. So the reason I knew it was inside, so Carrie goes, how do you know which way it was? The reason I knew it had to be inside of there was I knew that this p-value was 0.08. And mine was 0.05, so it has to be a smaller area. So I'm like, it has to be somewhere over here, just in comparison. I lost you with that.
No,
didn't?
I got it. I
Okay.
think it would just be like, at least for me, like I would be able to understand it more if we did on like two
separate graphs.
Yeah.
And the good news is, very rarely will I ask you to do both like I'm doing right now. So I agree. That's why I did the first one on two separate ones. I got a little brave here and did it all on one. Maybe it didn't work so well. Yes.
No, you already got the critical values now.
So where does my test statistic? My 1.75? Here it is. Make it nice and huge. Is it in my critical region?
No.
It's not in the green zone. It's not past 1.96. And it's not past negative 1.96. So if it's not in that zone, that's when we fail to reject H0. If it's in the critical region, we reject. If it's not in there, we fail to reject. So either way, we get the same conclusion. Either way, we get the same conclusion. Told you chapter 8, but you didn't want to miss this lecture. Imagine just trying to read out of your book. You could get there, but you don't have to ask questions, speed it up a little bit. Okay, so let's review a little bit about our steps. Step 1 was write the two hypotheses, H0 and H1. Step 2 is get the test statistic. These numbers that I've been handing to you, can't show you how to get those quite yet. Step 3 is either find the critical values or the p-value. That's what we've just been practicing. Get the p-value or get the critical values. Step 4 is to either fail to reject H0 or reject H0 based on your decisions, either one or the other. And then step 5 is to finally state the conclusion to the original claim that we started hours ago, or so it seems. So using some words that somebody could understand. What does your evidence show? Does your evidence show the guy's guilty or not? Does the evidence show the proportion really is something or not? So let's talk about those now. That's step 5.
What was step 5 again?
It's listed in the middle of page 106.
Oh, okay.
State the final conclusion about the original claim using non-technical terms. I don't want words like P0 and reject H0 and H naught. I mean, I want words that say whether or not you are supporting that original claim or rejecting that original claim. So if you look in the middle of page 106, I have it in bold and underline, which makes that mean it's really crucial. You can never support an original claim that is H0. That's similar to somebody going to court saying, I'm innocent. You can never support that the person's innocent. You can't. All you can say is, we don't have enough evidence to convict him. We don't ever prove him innocent. It just doesn't work that way. So the same thing is true here. If H0 is your claim, all you can do is reject it or not. That's all you can do. So if I go into court and I say I'm innocent, the jury's either going to say, yeah, I'm either going to reject your claim or I'm not going to reject your claim. But I'm not going to say, yes, you're innocent. It's either I convict you or I don't convict you. There's no, yes, you're innocent.
Step 5 is all about H1 then.
No, step 5 is all about your original claim. Which, remember when we started writing them, sometimes it was H0, sometimes it was H1.
Oh, okay.
So it depends. If H1 is your claim, you're either going to support it or not. So I claim that, let's say, let's go back to my coin problem. I claim it's a fair coin. Brian's back there going, no, Jill, I'm pretty sure your proportion of tails is less than 50%. So his claim is the less than claim. If I barely get any tails, barely 10%, we're supporting what he says. We're supporting that, yeah, it is actually something less than 50%. So if it's H1, you can support it. That's like you can convict, right? You can support the prosecutor, but not the defense lawyer. Okay, so let's talk about it now. And that's written there in that step 5 in sentence form. We can never support H0. All we can do is reject or fail to reject it. And then we may or may not support H1 based on what we have. So let's see if we can go through this. Example 9. We have a claim that the percentage of Americans who know their credit score is less than 20%. And our hypothesis tells us to reject the null hypothesis. And it wants to write the final conclusion. So someone's already jumped ahead to step 4 for us. I like to write my claims here just so it makes sense. In about, I don't know, 5 minutes, maybe 10 minutes, we're going to do one problem all the way through. 10 minutes we don't have, so maybe it'll be 5 minutes or next time, we'll see. But what is the original claim?
That less than 20% know their credit score.
Less than 20% know their credit score.
So it would have to go in H1.
Okay, why does it have to go in H1?
Because you can't put it equal to.
Because it's a less than claim, right? So it has some less than.
So P.
P, because we're talking about a proportion or a percentage. P less than 0.20. That's the original claim.
And then the complement would be P equals 0.20.
You okay with writing those? Writing those is crucial, otherwise you can't even come to a conclusion or anything. So the step 4, someone did step 4 and decided that we were going to reject H0. See where it says that? Reject the null. I like to use a visual here. Someone came along and said they have enough evidence to reject this claim. I cross it out, it's been rejected. If it's rejected, what can you say about my claim?
The evidence proves that.
We don't say proves, but you're close. We never say the evidence proves, but we say it supports it. So therefore, we must be supporting that claim. Because we rejected H0, so therefore we must be supporting. It's always one or the other. So we reject H0. So our final conclusion is that, I actually wrote it there, there is sufficient evidence to support the claim that the percentage of Americans who know their credit score is less than 20%. We always say there is sufficient evidence. If you're rejecting, you have enough evidence to reject. Or you say there's not enough evidence. There's insufficient evidence if you didn't reject. Read it again, make sure it makes sense. We have sufficient evidence to support this claim that, I lost my place, the percentage of Americans who know their credit score is less than 20%. There's no H0 symbols and p-values and alphas in that statement, though. Is that right with that conclusion? Okay. Let's do example 10 and write our own conclusion. So we have the original claim was that the percentage of non-smokers exposed to secondhand smoke is 41%. And there was a decision to fail to reject the null. We want to write the conclusion. So again, I want to write the symbols first. What was the original claim?
P equals 40.41.
You agree with Kirsty? She said P equals 0.41? Proportion again? So what was H1? It's not equal. And this one was my claim.
So then you have to support it.
You're close.
You reject it or not.
Yeah, and then it said failed to reject, right?
Yeah, so it's. Would you put something like
I can't hear you, Kirsty.
there's sufficient evidence to support the claim?
Not quite. We agree that I can't reject it, so I'm kind of stuck with it. I'm going to say I'm stuck with it. I didn't reject it, so I'm stuck with H0. The evidence, you always say you have sufficient evidence if you're supporting H1. So this is like going to court. I couldn't convict the guy. The guy went in there, he says he's innocent. I didn't have enough evidence to convict him. We're not supporting him. All we can say is we didn't have enough evidence to convict
Fail to
him.
reject.
So it's the fail to reject. So we say we have insufficient evidence.
Insufficient evidence.
We have, I like to say not enough. We don't have enough, let's use a little bit more English. We don't have enough evidence to reject the claim that, what was the claim? How about in words? Percentage or something?
Percentage of non-smokers, 41% of non-smokers are exposed to secondhand smoke.
I'll move out of the way here in a second. You could have just restated it exactly the way they had. I just rewrote it, so I was going off my memory. So when you reject H0, like we did earlier, that means you have evidence to reject. When you fail to reject, you don't have enough evidence to reject. Whether or not you're supporting or rejecting kind of depends on your claim. But we didn't have enough evidence to reject. Like my coin earlier that came up 51%, it's not exactly 50, so all we could say is, I don't have evidence that it's not fair. We're not saying it is fair, we said we don't have enough different to say it's not fair. Yeah.
So if HO is proven to be rejected or not, it's kind of like being acquitted. So you're not saying it's actual,
Yes.
but then it's, okay.
Beautiful. If you fail to reject H0, you're acquitting somebody. Yeah, you can go, because we couldn't convict you. It doesn't mean you're innocent.
Right.
We've talked about O.J. Simpson for hours in this class, right? He's a good one. People like to use that example. We could go on. Right. Okay, let's do example 11 real quick, and then we'll be out of here. This one's about a mean. The mean GPA is higher than 3.1. How do I write that? I want to write my claim first. Which one's my claim? One more, guys. One more, we can do it. H1?
Yeah.
What do I write?
It's H1 is what we're going to support.
Okay, but what do I write?
Okay, so you write
Go
M.
ahead, Brooke, what'd you say?
Mu is greater than 3.1.
Mu greater than 3.1, she says?
Yeah, and then mu equals.
Mean greater than 3.1? And mu equals 3.1. Which one's my claim?
The bottom.
The bottom one's my claim. And the decision was to fail to reject H0. Which means I'm stuck with this, and I don't have that. I failed to reject it, so I'm stuck with that assumption being true. We don't know this is true. Failed to reject H0.
And the null is the first.
The null is the fancy word for H0.
A null is like H0?
Yes, null is what we call H0.
Okay,
So what can you tell me about my claim? Can I support it or not?
No.
No.
Right, so what we say is, we don't have enough evidence. It is. I wouldn't use those words.
Put it in my lingo.
Well, it makes a lot of sense when you put it in, like, context of court.
I
Then
think
it
so
makes
too.
sense.
Support the claim that, what was the claim?
C
That the
students
GPA
have a higher GPA than 3.1.
Where's the mean in there? It's supposed to be there
The
somewhere.
mean GPA of LC students is higher than.
Okay. So before you go, I know you want to get out of here. I just want to make sure you're clear on one little thing. Higher than 3.1. When we say we do have evidence or we don't have evidence, when you're rejecting H0, and we're making this decision over here, that's because you have enough evidence to reject. So when you reject, you have sufficient evidence. If you're failing to reject, you don't have any evidence. We don't have enough evidence. Same thing like in court. So we didn't get to 8.2. We'll be able to get to it next time though. What we're going to do there is do this whole thing from scratch, give you a whole scenario to make some decisions. Definitely work through this lab, the online thing. Make sure you get this terminology down. I'll see some of you in the lab in a few minutes.